Hello, my name is Milo Šikić, and today I'm going to present you our work on HERRO, haplotype-aware error correction of outer-long nanopore reads. Actually, it can be used for any kind of simplex nanopore reads. It is not required to be only outer-long. So 7 years ago, we presented a method for correction of reads and assembly. And this method, called RACON, is quite popular. And but unfortunately, today the requirements are different. So when we developed it, we didn't need to take care about phasing genome. So at that time, having haploid collapse genome was okay. And today, the requirements is that we try to achieve telomere to telomere genomes. So that means that we need to try to correctly reconstruct all repeats. So if we have many segments in repeat, we needed to reconstruct all of them. And to achieve this, assemblers use information from each of segments because there are some teeny differences. So we would like to keep this information intact during the correction. The second thing is today we have phased genomes, and we would like to keep information which are important for phasing intact as well. So that was a new challenge, and we tried to achieve this. So the standard approach for correction is to have a read and then overlap all reads to that one. And after we have all of these overlaps, we will split them into windows. And in each window, we will try to find the multiple sequence alignment. And once when we have the multiple sequence alignment, we will just stitch all of these resolved windows together. However, for HERRO, we needed to use some AI to try to not correct this important position in segments or positions related to haploids, and we call these positions informative positions. So the pipeline starts with read pre-processing, which includes trimming, splitting, filtering and removing all kinds of adapters. After that, we have over-resolve alignment using Minimap tool. And at the end, we use some AI models to try to recognize all these informative positions so that we do not overcorrect them. HERRO works for both R9 and R10 chemistry. The requirement is that we use reads longer than 10,000 nucleotides and with quality value above 10. To keep informative position intact, we developed the special type of a model. So it consists of two types of neural network architectures. So we have two convolutional layers, and at the end we have an transformer encoder block. So the idea is following. So for each position in a read, we see alignments to this position, and we will try to find positions that could be potentially informative. How we will define them? So the potential informative positions are those positions that have, for example, two types of nucleotides supported for these positions, and for each of them, we should have at least 3 or more reads that support that position. And the idea is the following. We have reads. So we take 31 read per window. Window size is 4,096 nucleotides. So we have windows long enough, so if we have several potentially informative positions, they can support each other. In the first convolutional network, we just take the representation of each read. And in the second convolutional network, we take the representation for each position. It is important to mention that we take representation only for those positions that are potentially informative. After that, we feed this representation to transform encoder block, and at the end, we have fully connected layers where we try to predict two things. If the position is informative, so if position is not informative, that means that we can correct its position. And in that case, instead of letter or nucleotide in original sequence, we will replace it with predicted corrected sequence of one or more nucleotides, or even we can have deletion. So it is important to mention for all other positions we use the majority vote. We can correct indels up to 30 nucleotides long. And what is important that we need to have a high quality reference. So that's the reason why we use HERRO2, and we trained on just 5 chromosomes, 1, 2, 17, 18, and 20. So here you can see some of our results. So you see 2 images. On x-axis, you can see read qualities before error correction, and on the y-axis are after correction. And I would like to highlight this is the concordance quality values. That means that they're achieved by mapping reads to the reference. So you can see that results improve significantly, especially if you take into account that values on y-axis are actually in logarithmic scale. So you can see results for chromosome 9 of human genome not used in the training. You can see also results for Arabidopsis, completely different genome. So we never seen Arabidopsis in our training. You can see results from zebrafish and another human genome, CGM13 for R9 reads. It was important for us that HERRO supports also other chemistry so that people can correct their already sequenced reads. Here you can see again results before and after correction. So in blue are results before correction, and in orange are after correction. And you can see the whole distribution for all chromosomes of all reads. And it is evident that the quality value improves from 20 to almost 40. So it is almost 2 orders of magnitude, 100 times improvement in accuracy. Here we just show how the results and how HERRO can be used for error correction and then de novo genome assembly. You can see 5 results for 5 genomes here. So the first 2 are diploid genomes, HERRO2, and our internal genome of and Singaporean of Indian descent. And this genome was resolved telomere to telomere with quality value of 70, so we can use it for assessments, and it is of high quality. And we also use several other high quality genomes like CGM13, haploid human genome, and 2 other haploid genomes, zebrafish and Arabidopsis. We use the HERRO as assembler because here we present results for HERRO because it reconstructed almost in each run chromosome X and Y, and it is amazing results. HiFi can be used as well, but in the case of HiFi, we needed to chop correct reads. And that's the reason, and the fact that HERRO always resolved chromosomes X and Y to present this result with HERRO. But if you want to do it faster, you can use the HiFi. And for haploid genomes, we use the LGA. So it is also the way how you can represent haploid genomes. So in accordance with our assessment, LGA outperformed other tools. When we try to increase the coverage, so I would just like to mention that the minimum coverage from here it's about 40x. So if you increase coverage, results are even better. You can see more reconstructed chromosomes telomere to telomere. Here you can see very interesting regions. So rDNAs, the rDNAs are the last region we need to resolve. So this is one of our DNAs we resolved correctly for one chromosome on our Indian genome, and we try, and you can see here the error rate of reads when we try to map them to this region. So in the first row, you see HiFi reads. In the second one, you can see Nanopore ultra-long reads. I need to mention that here you can have reads from different segments. You can have reads from mother or father. So that's the reason you see different error rates for each of reads. And in rDNAs, differences between segments are very, very teeny, and many chromosomes, 5 chromosomes, across-sencting chromosomes, have these regions which are very, very similar. And in the third row, you can see results after error correction. So you can see that we solved almost all errors, but sometimes we do overcorrection of some positions. So our method is still not perfect, but I believe it is good enough. And we are aware that sometimes we overcorrect, but mostly these errors are in homopolymer regions, which are really difficult, even for all sequencers. And finally, I would just like to highlight some results that we've seen, and it is important to have high quality reference. So here you can see assessments of read quality when we map them to their reference built from the cell line. So in the first row, you can see H02 reads when we map them to H02 reference and some other references. And you can see the error rate is very, very low when the same reference is used, but the error rate is higher when we try to use other references. So and you can see that the error rate, mismatch error rate is around 0.2, and the total mean error rate that includes both mismatches and indels are around 1%. So it should be very careful when we train model, when we assess models, to take care about the right reference. Without this, HERRO would not be possible. So HERRO is available as a preprint at bioRxiv and on GitHub. And I would really like to emphasize the role of Dominic, who developed this tool, who did testing. It would be not possible without great help from Sergey Nurk, who helped us with so many details. I remember our first meeting when we started working on this. So we tried to start with the shortest human chromosome, chromosome 22, and Sergey mentioned us, no guys, never try to use acrocentric chromosomes because of these rDNAs. Even if this one is the shortest, this is not a good idea. And also, I really like to highlight the role of Paula. Paula and I started this project, and without Paula, this would never happen. And she has helped us a lot during the whole project, helping us with data sets, with comments, and her role was really invaluable. And I also want to mention Chiachi, who prepared these results for rDNA, and in the end, the project was jointly funded by AI Singapore and Nanopore. And finally, my favorite photo from a bar in Croatia, and you can see on the left Robert, in the middle is Dominic, on the right is Ivan. Robert and Ivan are first author of RACON and the first error correction tool, and now in the middle is Dominic, author of HERRO. Thank you a lot, and you can contact me anytime related to HERRO.